So it's going, and what I've got now, I just want to kind of go over this because I just had you guys build 2 circuits. And one of these circuits, something like this, 3 light bulbs, okay, in series. And one of these circuits looked a little more like this. And we've got 3 light bulbs in parallel. So there's negative battery voltage up here, right? So where did you guys put the switch?
Anywhere it would fit.
Beside the battery.
I put it on the leading side.
On which side?
The leading side, the one where positive.
So you put your switch up here on positive.
Yep.
All right.
I don't remember the term for when you put it before the load.
Okay, so this is before the load. All right. So when we consider this, what I've got is a power side switch, which means it's before the load. Okay. And on both the series and the parallel circuit. So what I kind of want to go over today is you guys have some familiarity with that. And this is the kind of thing in particular that you were dealing with when you were looking at your taillight circuits and things like that, okay? So what if I have something that looks like this? So I've got my positive here, okay, and I come down and I come into an actuator like that, okay? And then I go from the actuator down into something that looks like this. You see the switch is no longer on the power side. The switch is on the ground side, okay? This right here is very, very common in any computer controlled or processor controlled circuit, where we don't switch power on and off, we switch ground on and off. And let's say this is a fuel injector. If I've got a 4-cylinder engine, then I have 4 fuel injectors. And so this is a fairly generic, but fairly typical diagram for something like that. Okay, now, these symbols here are inductors. They use an electromagnetic field to move a ferrous material up and down, okay? So when I have an electromagnetic field, I pull the ferrous material up, and then if I've got fuel going through these injectors, when that ferrous material moves up, the fuel is injected. When the material moves down, the fuel stops flowing. So I bring these down, and each one of these has inside my computer a ground switch. So this is ground side switch, and this is an ECU or PCM or ECM or whatever it is your manufacturer calls it. Electronic control unit, powertrain control module, engine control module, whatever. Okay? And if you look at the structure of this circuit and this circuit, they're both parallel circuits. So when we consider a parallel circuit, and I'm going to use simple numbers, okay? If my battery voltage is 12 volts in a parallel circuit, that means I have 12 volts on each one of my branches. Okay? So the 12 volts is constant at each branch. Now, if I tried to do this in this type of a circuit here, I'd have a bit of a problem. So, if I built this fuel injector circuit and I'm driving 2 injectors, okay, like this, and it doesn't matter if it's ECU controlled or not, there's a couple of things here. All right, number one, I have one control for 2 components. That means both of these are going to have to turn on and off at the same time. Over here, I can turn these off and on individually, okay? Because my switches can be controlled individually by my powertrain control module. Here, I can't control them individually. Number 2, if I have 12 volts available here, each one of these resistors is going to use a different amount of voltage based on the resistance. So what that means is this one splits voltage and this one splits voltage, and the 2 voltage amounts will add up to 12 volts, but each individual part is receiving less than 12 volts. So if I have a component that requires 12 volts at some amperage to operate, without that voltage being present because they're stealing voltage from each other, they're not going to operate properly. Okay? Now, this is technically a parallel circuit because there is most likely a common ground here. All right? That ground may be internal to the module, but there's a common ground. So we could see now, with 4 switches, I can control these as necessary. So let's say that I have a firing order of 1, 3, 4, 2. So now we need to kind of go back and think about our engine events. So number 1 is going to get to the top of compression and then power stroke. Then number 3 will get to the top of compression and then power, and so on down the line. So what that means is that if this is number 1 cylinder, this is 2, this is number 3, and number 4. Number 1, number 2, 3, 4. Then this switch will close and open first. This one will close and open second. This one will close and open third. And then this one will close and open fourth. That way, each one of these injectors is cycling in time with the cylinder event that's occurring. Okay, this is what's known as sequential fuel injection. So, when I'm looking at all of this, this is a pretty straightforward circuit. I've got shared battery voltage coming from a source on the vehicle. Maybe it's a fuse, maybe it's a power hold relay, who knows? Depends on the manufacturer. But that voltage is common. Then we come down here and we start doing this. Thinking about, again, the firing order and the order that we're going to cycle these things, there's another factor that we need to take into account. And that is, how fast is the engine running? Okay, if I'm at 800 RPM, then the time between each one of these cycles is going to be different than if I'm at 3000 RPM. This can occur much more slowly. At 6000 RPM, I have to cycle these injectors in this order even faster. Okay, So at 800 RPM, maybe my injectors are looking like this, and at 3000 RPM, they're looking like this, and then at 6000 RPM, they're looking like this. Okay? So we see that the amount of time that our injectors are on and off for gets increasingly smaller as engine speed increases. It has to. We could stay with the slower rate, but it's not going to be terribly efficient. All right, so this is going to speed up, and not only are our fuel injectors doing this, but in the gasoline engine, our ignition coils are also doing this. They're also speeding up. If we've got individual coils in particular, they're going to follow something that looks like that. A diesel engine, it's purely going to be this. All right, so how do we make that happen? What are we looking at that makes this occur? When we have an engine running and it's computer controlled, we're looking at some load indicators to determine how our fueling and spark ignition is going to occur. I'm mostly talking about fueling because fueling goes between both gasoline engine and diesel engine. Okay, so this applies everywhere. So if I'm looking at that, then RPM, my sensor for that is crankshaft speed. Okay, and then another load is going to be throttle position sensor. And this one's critical because this is telling the computer how much gas, how fast does the driver want this thing to go at a particular, for a particular mile an hour in a specific gear. So I have crankshaft speed, throttle position, and this is a load sensor, okay, and this is driver demand. And then I might have, over here, I'm going to say mass airflow. But there are some other ways that we can also calculate the load of the engine demand. And what this is how much air is actually entering the engine. And the amount of air entering the engine ties directly to throttle position. And throttle position ties directly to crankshaft speed. So how do we know? Keep in mind, this PCM here is responsible for turning the injectors on and off. This is what's known as an injector driver. Each one of those has a driver. Well, what if I have something that looks like this? It's a magnetic pickup. Okay, so I've got on my crankshaft here, keyed onto my crankshaft, is this trigger wheel. And this trigger wheel is rotating with the crankshaft. And as it rotates, it comes up to this magnetic pickup. And it comes to the magnetic pickup, what happens is it creates a magnetic field. And then as it rotates past it, and this flat comes to it, okay, that blank part, then the magnetic field collapses. And each time I create and collapse that magnetic field, I induce some current, right? So, this crankshaft speed sensor here is this part, and it sends a signal over here to the PCM and the ECM. All right, and in this case, the signal it's sending is time. How fast is this thing turning? All right. Additionally, I can also manipulate this. So now you see I've got these narrower openings and I've got one big opening right here. See that? So what happens is I'm creating this voltage. And this voltage looks like this. And this is slow RPM, and this is really fast RPM, right? But each time this blank comes by, I get something that looks like that. See that pause? All right, so the processor says, here's the frequency of this sensor input, that's the time, okay? It's occurring this often. And here, I've got this opening, so that means that maybe the next pulse I'm gonna get is number 1 cylinder. So that means that when I get to that pulse, I know I'm back to this point in my order. Does that make sense? And then I can speed this up or slow it down based on the period or the amount of time. Is that okay? This right here is a feedback loop. And this is just one section of a feedback loop. When we're looking at a modern processor, it's looking at a tremendous amount of data. There's all kinds of sensors that are telling the processor what's going on with the engine RPM, with ambient conditions, with driver load and demand, with vehicle demand, vehicle load, vehicle gear. We're looking at all of these things. Not all that information comes flying into the PCM, the ECM, or ECU, and the programming within the PCM, ECM, and ECU tells that the logic, the thinking part of it, that it needs to react in such a way based on this input. Then it makes these changes. Okay? Again, this is just the fuel injection. A lot of time, we also look at camshaft position for fuel injection. So we're camshaft and crankshaft, we're really monitoring that to know when. Okay, we might look at differences in rotational velocity between camshaft and crankshaft to gain an understanding of possible misfire, things like that. All right. There's all kinds of stuff we're looking at. This is a feedback loop. And this is what we're going to be exploring over the course of the next couple of days. Getting some familiarity here. All right. Now, the last thing on this is my RPM right here is going to drive this. My driver demand and engine demand is going to drive what's known as a pulse width. And what that means is that I can vary my on time in relation to my off time. So that means that if I want a lot of fuel, I can have a lot of on time versus a very short off time. You following that? If I want very little fuel, then I have a lot of off time in relation to a short on time. And we pulse width an awful lot of stuff because it gives us very precise control. Okay? And these pulse widths, they're actually occurring at faster or slower rates based on the RPM of the engine. We pulse width a lot of stuff. Now, this may very well become dinosaur technology, since we have so many state governments that are mandating electric vehicle sales and the phasing out of ICE or internal combustion engine sales. One area that electric vehicles are not super effective in yet, though, is heavy truck. Okay? Because when you start talking about heavy truck, there's still issues with the fact that the electric vehicle, the amount of time that it charges versus the amount of time that it discharges under heavy load is still not real efficient. So while we may see that we'll lose opportunities in the gasoline engine market for technicians, the diesel engine market may survive a little longer. Okay? So there you go.